We're going to tackle this big green monster called stoichiometry. Stoichiometry is Latin for cooking. No, never mind. No, it's not. But I like to think of it as a recipe. When you cook, you need to know what you put in. You need to know how much you put in. It tells you how much you get out. And if you want to change the recipe, you need to change it by increments of the same ratio. So double the recipe, great. Cut it in half, great. Cut it into thirds, great. The ratio stays the same even if you're using more or less. And that's what stoichiometry is really about. First, we need to be able to just do the mechanics of stoichiometry, which I call going through the 4 boxes. So here's 4 boxes. The actual stoichiometry is really from here to here. Just moles of A to moles of B. A is going to be what you know. It can be a reactant or a product. It's the amount of a reactant. It's the amount of product. And B is what you're looking for. So it's the question. You may be looking for how much of the reactant you need, or you may be looking for how much product can make. But moles of one to moles of the other is stoichiometry, and we're going to use coefficients from the balanced equation, which means we need a balanced equation. Now, this 4 boxes are going to be a dimensional analysis. So to go from the first box to the second, it's going to be 1 hop, 1 conversion. Second to the third, 1 hop, 1 conversion. Third to the fourth, 1 hop and 1 conversion. And the reason why this is nice, because you may be given all sorts of things. You may be given moles, you may be given particles or liters. You may be asked for moles, you may be asked for particles or liters. So this helps you kind of guide you where to start and where to go. In pedagogy, they call this a graphic organizer. Super fancy. So let's try one question here. This says 5 liters of oxygen completely reacts below. How many moles of iron 3 oxide can form? I like to put the stuff I know underneath here. So underneath the oxygen, I'm putting down 5 liters. And then underneath the iron 3 oxide, I'm putting down question mark moles. So since the liters are given, this is A. Since we're asking for moles of iron 3 oxide is B. Now, looking at the 4 boxes, where do we start? Well, they give us 5 liters, so we're going to start with liters. So we're starting this box. And where do we go? Well, we're going to go, A is going to be oxygen, so we go from liters of oxygen to moles of oxygen. And then moles of oxygen to moles of the question, which is iron 3 oxide. And in fact, that's the question, so that's all we have to do. We do 2 conversions, and this helps you figure out that you start with the first one and go to the third one, not the fourth. We don't start in the second one because of units of measurement. So let's just write this out. We're going to have 5 liters. Oh, I'm under the assumption at this point you can do mole conversions, you can add up formula weights, and you can balance equations. Okay, so we're going to convert the liters of oxygen, liters of A to moles of A. So that's going to be 22.7 liters of A, which is oxygen, to moles of oxygen. Then, just like our alt dimensional analysis, you got moles on top, moles on bottom. Moles of O2 going to moles of Fe2O3. I'm squeezing it in there. Now, this says we're going to use the coefficients. There's a 2 and there's a 3, and that's what we're going to use. We're going to use the 3 in front of the oxygen and do that, and the 2 in front of the iron oxide. Because in terms of particles, this is a 3-to-2 ratio. 3 moles of oxygen will be used up when 2 moles of iron oxide are formed. And when you do the calculations and round to 2 sig figs, because of the 5.0, you get 0.15 moles of iron 3 oxide. That's the answer. Let's do a new problem using the same balanced equation. So let's say that we need to make 15 grams, 3 sig figs there, 15 grams of iron oxide. And we want to know how many liters of oxygen do we need. Now, this is a product, but this is going to be A, and we have grams, so we're going to start here with grams of A, and this is going to be iron oxide. And then we're going to go to moles of iron oxide, and then moles of whatever's asked, which is the oxygen, and they want liters of oxygen, so we do one more. So that's all the way through the 4 boxes. That's going to be 3 conversions. Let's see if I can squeeze it in here. The formula weight is going to be 159.7 grams for 1 mole. This is going to be iron to oxide and iron to oxide. And then you get iron oxide on top, iron on the bottom. This is where we use the coefficients. So we're going to have a 2 to 3 ratio. It's moles of the oxygen. And again, we're going to the oxygen because the question dictates it, not because we just want to or you know to. And then I'm going to get rid of this guy over here, and we're going to go to liters. So for liters, we're going to have moles of oxygen on top, moles of oxygen on the bottom. 1 mole equals to 22.7 liters of oxygen. And if you do the math, you end up with 12.8. 12.8 liters of O2. So this is what I call just running through the 4 boxes. There's not a lot of evaluation or anything like that. And we'll talk about this in the next section. But when you do stoichiometry, it's more like an if-then, right? So if-then. So if we need this much, then this is how much we need to use. It doesn't mean it actually happens. But if we do want this much, this is a minimum of what we need. That's if we don't lose any or anything else. So when we do the math, it's not guaranteed that's what's going to happen, but that is the maximum amount. And that's stoichiometry in a nutshell. The next video we'll talk about when it gets a little more complicated, but we'll still do the same going through the 4 boxes. We just need to do it multiple times. And we have to use this concept of if this is the amount that you used up, or if this is the amount that's going to form, we have to realize that means it may not. So we'll see you in the next video. I know you're super excited about this stuff.